a ring, a current carrying wire like this. So now that we learned how to do anywhere in the center, so now let's learn how to do anywhere a certain distance x away. So you see, now we learned this way, how to do it here. So now any sort of axis x away. Okay, so we're going to kind of approach this the same way that we did for the electrical field. We're going to take a piece of the wire here with the current coming out towards us. You see, the current is kind of coming like this, out of the board, into the board, out of the board, into the board. Here it's going into the board. So take those two pieces and say, what's the magnetic field created by those? So this is r hat. So then you go like this. The field is coming toward you, the current. Then you curl it in the direction of the r hat. And then your thumb points in the direction of the B field like this. You see? So go like this, out of the board. Face your palm in the direction of the r hat. So tilt it slightly. And then curl it. And your thumb is perpendicular to the direction of the r hat. You see, like that. And then this guy, go into the board, curl your fingers in the direction of the r hat, and then your thumb points in the direction. So it goes like this. dB is like this. So you can kind of see it's perpendicular to the line of sight. Okay, so then you say their x components cancel. The y components cancel and only the x component survives. So dB, dB is going to be 2 dB. This is theta, 2 dB cosine theta, dB total. Right, and then dB total 2 mu 0 I over 4 pi, and then this is going to be dl, and the angle between the dl and the r hat vector is going to be 90 because the dl is coming out of the page, so that angle there is 90 degrees. You see, so 2 mu 0 I dl over 4 pi over r squared cosine theta. And now you're going to say the r squared is going to be x squared plus r squared. X squared plus r squared. And then cosine theta, well, this theta, oops. Why it appears? Oh, I see. It appears a weird reflection. So theta is going to be, this is 90 minus theta, this is theta, this is 90 minus theta, and this is theta. So if I want to know what cosine theta is, I have to relate this theta to this triangle. So I have to be careful when I relate them. I say this is 90 minus theta, this is theta, and then this is, right here is 90 minus theta, then this is theta. So when you do cosine theta, it's going to be the radius of the ring time over the r. Radius of the ring over the, another one of these r's. Right. So this is just r. So another one of the r's. So you just get a half, 3 halves again. Okay, and then you integrate that over the full circle. Oh, actually over half the circle, because I've already doubled it. So remember, I took a piece from there and took a piece from there. And yeah, so then I already counted for double. So when I integrate this over half the circle. So it ends up that it's actually not an integral. So you're just going to take everything out of the integral. Then you're going to get mu 0 I over 2 pi r x squared plus r squared to the 3/2, and then integral over half the circle of dl. And then that gives you pi r. And then you're going to have this pi cancels. Okay, so then you're going to have mu 0 I r squared over 2x squared plus r squared to the 3/2. Okay, so let's see if this answer makes sense. If the answer makes sense, if I put x is 0, what should I get? When I put x is 0, I should get the magnetic field for the center of a coil. Well, we already know that it's mu 0 I over, so the center, I already know what to expect. Mu 0 I over 2r, right? So if I put here x is 0, what do I get? X is 0, mu 0 I r squared over x is 0, so you get r squared to the 3/2. And then, of course, 2 cancels. R squared over r cubed. Aha. That gives you the same thing we got for the magnetic field of the center of a coil. You got it. Cool. Okay, so then using the magnetic field of a, this could be called the magnetic field of a coil in the central axis of the coil. You see? So we could also use this to calculate the generalized magnetic field of a solenoid. Generalized magnetic field of solenoid. So I think we're kind of near the end of this section. What's left to do is the generalized magnetic field of a solenoid and also the magnetic field of a plate, a charged plate that's spinning. So now the generalized magnetic field of a solenoid is essentially a coil like this, but it's kind of like the helix that we studied earlier. It's like the current is coming like this, and then going back, and then coming down, then going back, coming down. So basically, you're wrapping it around some cylinder, let's say. You're wrapping a wire around the cylinder like this, and then you keep doing that, you know, like that. And then you want to find the B field, let's say at the center or at the edge or even anywhere outside of the solenoid, you know. That's kind of what we're looking at here. Magnetic field, see this one here? Magnetic field of a solenoid. So for a long solenoid that's much longer than its radius, the magnetic field of the solenoid is mu 0 Ni. This is called the long solenoid approximation. You see? Mu 0 Ni. Now, the usual way to prove this formula is to use Ampere's law, which I'll probably show you tomorrow, is the Ampere's law method. This is kind of what they do. They do an Amperian loop. You do an Amperian loop around the solenoid, and you apply Ampere's law to that loop. And then the derivation is so quick. BL is mu 0 Ni. B is equal to mu Ni, and then you bring the L down to the bottom, and then that's it. that's all you need is mu Ni, and then the little n is N over L, and that's the derivation. Magnetic field of a solenoid. But we should be able to calculate that using our general technique, right? So calculate the magnetic field at the center of any solenoid. So let's start doing it this way. Let's call this 0 and let's call this L. Let's put the axis here. Okay, so then I'm gonna say, let's say I want to find the magnetic field at some location, let's say some distance d away from the edge. So it's kind of like doing the rod integral. So imagine, treat the solenoid as a rod, and let's say the length of the rod is L, and this is D. So I said, let's take a piece of the solenoid with a current Di, right? So what is the magnetic field created by that solenoid, by that piece of the solenoid at that location? So we have the equation here. The B, so the magnetic field created by that piece would be mu 0 I. R squared would be the radius of the solenoid. So that would be this one here, over 2. And then X would be what? It'd be the distance from here to here. So from here to here. So if I'm putting my XY axis here, this is my X. So the X that I need to put here should not be this X. It should be the distance from where that piece of the solenoid is all the way to that point. So that's the X that I should go here. So what would that be? X plus, let's see here, X plus, this one would be from here to here is L, and then from here to here is D. So L plus D is equal to, or let's call this R, right? And then this is going to be X. L plus D is X plus R. So R is going to be L plus D minus X. Okay, so in other words here, what goes is that we want to know the distance between any piece of the solenoid and that point. You see, so this one right here, this R, you see. So that's what I'm going to put there. And then so this is going to be, R is going to be L plus D minus X quantity squared, right? That's going to be this thing, right? Plus the R squared to the 3/2 power, right? And let's see. Oh, and then the current is going to be Di, and then Di is going to be lambda dx. So mu 0 lambda dx. Okay, so then I'm going to integrate this. D is going to be mu 0 comes out, lambda comes out, R squared comes out, 2 comes out, and then I'm going to integrate dx over L plus D minus X squared plus R squared to the 3/2 power. Right, and then what is lambda? The lambda is the current density, which is how much current there is divided by the length of the solenoid. So it just be I over L. No, actually it's Ni over L. Number of turns number of turns in the solenoid. So that would be the current density lambda, the number of turns times the current over the length, mu 0 r squared. So now if I want to see, let's say if my equation is right, then I put d is equal to negative L over 2, right? That means I am inside of the solenoid, negative L over 2. Then I put that here, negative L over 2, and that gives me a general equation for the solenoid at the center of a solenoid. So then what's that integral come? Dx over L minus L over 2. So that's going to be L over 2 squared plus r squared to the 3/2 from 0 to, and then your limits of the integral from 0 to L. Okay, here goes. Let's see what we get when we do that integral. I'm going to try a general variable integral without numbers. I think we should be able to get that. So now you're going to go squared plus r squared. Okay, L over 2 minus x squared plus r squared to the 1/2 from 0 to L. Let's see. Boy. Wait, is that the answer? Oh no. 2L over so let's write that down. Magnetic field at the center. So 2L over r squared square root of 4r squared plus L squared. Is that exciting? Huh? Yeah, is it? Well, not yet. There's no eureka moment happening yet. Okay, so that's kind of what happened. So I gave you the general equation to derive the magnetic field anywhere. You could also do this with numbers, of course, but what I'm trying for now is to see if the general result comes out to be the same thing that's derived by Ampere's law usually. You've seen that one derivation, Daniel? The one where you do an Amperian loop?
Oh yeah, I mean, that's the one that's always usually introduced to us with solenoids. We usually don't do it like this.
Yeah, you see, you do an Amperian loop, and you apply Ampere's law to that Amperian loop, and then you get B is mu 0 n I over L. And then that's usually written as mu 0 little n I. So that's for usually when the length of the solenoid is much bigger than the radius. That's the equation that we saw on those websites. So what I'm seeing is if the general equation, when I find the magnetic field in the middle of any solenoid of any length and any radius, if the general equation is going to give me that equation or not. You see, so that we're almost there. So then this 2L going to cancel with this 2L. And the R squared is going to cancel with the R. Now we can apply the assumption that the length of the solenoid is much, much bigger than its radius. Let's say the solenoid is much longer than the thickness of the solenoid, right? So then what happens? So the same technique like we've always applied, we say when this is bigger, this thing disappears, and you're just left with that. Now you have mu 0 Ni over square root of L squared. Aha! Eureka moment! Now, how about the magnetic field at the end of a solenoid? Mu 0 little Ni, you see? How about the magnetic field? At the end is kind of, I'm talking like in this area. You see how the field is already starting to move away from each other? So they usually say the field here is about half as strong as here. So it's starting to diverge. I'm not sure what the, let's see here. Magnetic field of solenoid at ends. At end. So let's see what their reasoning is. This is the kind of the easier reasoning. Magnetic field at any, oh, let's see here. Oh. It's kind of a ballpark approximation reasoning. It says magnetic field at any point is the summation of the magnetic fields produced by each turn of the wire of the solenoid. Now imagine the solenoid in front of you stretching to infinity on both the sides, say from left to right. The field at this end is now due to half the total turns, and hence it is E over 2. Huh? Oh, okay, so their argument is that the field here should be half the strength of here, because if you elongated this solenoid to like the left side, the field there would have been due to the field here and due to the field there. Oh, you see the reasoning there? It's like a ballpark, but it's a smart reasoning. That's actually, that's a funny reasoning, but it makes sense. It's like saying, if you have a long solenoid and then you have another one long on the left side, the field there would have been due to this guy and that guy. Well, now if that guy is missing, the field here should be half as strong. You see that, Daniel? What a quick, easy reasoning. So you see, it's a ballpark approximation to say the field here is half as strong as here. Okay, well, how do we do that officially with our method? We put D is equal to 0 instead of negative L over 2, right? Because D is 0 is right at the edge. Okay, so if D is 0, then what do we get? Then you just get 0, then you get L. Oh, so we just go back and reintegrate. So this would be the official way of doing that. So then just integrate L. And that's it. Let's see what happens. Oh, so we get L over R squared. We don't have the 2L. The other one was 2L over R squared. Aha. The other one was 2L. So we basically get half of, the integral comes out half of what it was before. Oh, then there you have it. If the integral comes out half, you're just going to have, instead of 2L, you're just going to have L, and then this 2 isn't going to disappear anymore. The L disappears, so you're going to have an extra 2 in the answer on the bottom. So this is at the end. Okay, so then you're going to say, okay, so this would be the general equation for any radius and any length at the end. Now you're going to make the same argument. You're going to say, if L is much, much bigger than R, this thing disappears, and then you get B at the end is mu 0 Ni over, and then you get this extra 2. Aha. So their argument holds pretty good. Nice.